As a nation, we eat a great deal of breakfast cereal, and one of our favourite breakfast cereals is a bowl of cornflakes. But as with many household commodities, there's more to selling cornflakes than a wall full of brightly coloured packets at the supermarket. It's a subject of serious market research. How many packets does the average family buy? And can they be induced to buy more? Some years ago, the Journal of Market Research published some data about the cornflake consumption of 491 families over a period of 24 weeks. You can see that 193 households didn't buy any packets of cornflakes at all. 71 households made one purchase, 49 made two purchases, and so on. Now, the purpose of doing a study of a sample of households is to use the data to make inferences about the population as a whole. For example, we might well be concerned with the mean number of purchases for the entire population. But how do we make such inferences? Now, we've already seen one way of doing that. The obvious thing to look at is the mean number of purchases, x bar. And if we're to use that to make inferences, we're going to need to know its sampling distribution. We'll be looking at a sample of size 491. And we've seen that if the parent distribution is normal, we can say quite a lot about the sampling distribution. If the parent distribution is normal, with mean mu and variance sigma squared, then we can look at the sampling distribution of x bar for different sized samples. This is the distribution for sample size 2. The mean is the same as for the parent distribution, but the variance is halved. If we continue increasing the sample size, the variance continues to reduce, but the mean of the sampling distribution remains the same. You can see that as the sample size gets larger, the sampling distribution becomes more and more concentrated about mu. That confirms the intuitive feeling that it's better to use a large sample than a small sample when we want information about mu. So that's what happens if the parent distribution is normal. In fact, we can be quite precise about this. If the parent distribution is normal, with mean mu and variance sigma squared, then the sampling distribution of x bar is also normal, with mean mu, as before, but variance sigma squared over n, getting smaller for larger n. And so if we know that our parent distribution is normal, we can use this result. But is the distribution of cornflakes purchases normal? Obviously, it can't be, because it's discrete. But does it have a similar shape to a normal? We can get an idea by looking at the data for our sample. If we plot the data as a histogram, then it doesn't look even remotely normal. In fact, it's exceedingly skewed. And we can calculate the skewness and pointedness of this particular data set. We get the skewness to be 2.30 and the pointedness to be 9.38. Whereas, of course, for data from a normal distribution, we'd expect values of 0 and 3. We can certainly conclude that the parent distribution is some way from being normal. So that leaves us with a problem. We don't know what the parent distribution is. And although we might be able to find out, it certainly won't be normal. So we can't use the theory we've developed so far to give us the sampling distribution of x bar. But it would be nice to have some idea of what the sampling distribution of x bar might look like. So let's take some theoretical parent distributions of different shapes and see what we get.
I've chosen two continuous distributions that are familiar to you, both of which have a shape that's very different from the normal distribution. The exponential distribution has a PDF that's very skew, and the uniform distribution has a flat PDF that's restricted to the range 0 to 1. Let's have a look at the sampling distributions of x bar for different sample sizes. First, we'll take the exponential distribution. This is the PDF of x bar for samples of size 2 from an exponential distribution. It's no longer J-shaped. It's equal to 0 when x bar is 0, but it's still very skew. Now here's the PDF for samples of size 3 and 4. As the sample size increases, you can see that the sampling distribution becomes more and more concentrated about the population mean, and also that it's getting much more symmetric. So, if the parent distribution is exponential, the sampling distribution for n equals 10 looks like this. It looks fairly close to the PDF of a normal distribution, and if we superimpose the appropriate normal, we can see how close they are. With n equals 10, the distribution of x bar is still somewhat skew, and if we look at the coefficients of skewness and pointedness, we get skewness 0.63 and pointedness 3.6. Still some way from the 0 and 3 of the normal distribution, but starting to approach them. But of course, the exponential is just one distribution, and it could be a special case. So let's look at the sampling distribution of the mean of the uniform. Here's the parent distribution. And here's the sampling distribution for the mean of samples of size 2. For samples of size 3, it already looks similar to the PDF of a normal distribution. And if we increase the sample size, we see the sampling distribution concentrating around the mean, a half. Again, we can compare the sampling distribution for n equals 10 with a normal distribution. The skewness is 0, and the coefficient of pointedness is 2.88, very close to the value 3 for a normal distribution. So, for two theoretical distributions, we've seen that the sampling distribution of x bar becomes more concentrated around the population mean as the sample size gets larger. We'd certainly expect that to happen, but what's much more striking is that the shape of the sampling distribution gets closer to that of a normal distribution. And that's no coincidence. We've been demonstrating one of the most famous theorems in statistics, the central limit theorem. Essentially, the central limit theorem says that whatever the form of the parent distribution, provided it satisfies the simple condition that its variance is finite, then the sampling distribution of x bar will tend to a normal distribution as n increases. It will have the same mean mu as the parent distribution, and its variance will be equal to sigma squared over n. As you've seen, with variance sigma squared over n, the distribution is tending to concentrate at the point mu for large n. So it's often convenient to present the theorem in its standardized form. The standardized variable z is x bar minus its mean mu and divided by its standard deviation, which in this case is sigma over root n. Then z has mean 0 and variance 1, and its distribution tends to the standard normal as n increases. Now this statement of the central limit theorem is in the unit, and its proof is technically quite complicated. So instead of presenting the proof, we're going to try to convince you that the result is plausible.
Well, you might already think the result to be plausible after looking at some PDFs. But what we've shown you so far is just the result that x bar is approximately normally distributed. In fact, since x bar is obtained by summing the random variable, the result means that a sum of such random variables is also approximately normally distributed. But we haven't explained why that result comes about. So what I'm going to do now is take a very simple case and try to explain why the sampling distribution of the sum looks like a normal distribution. Now, the simplest example I can think of is tossing a coin. If it's a fair coin, then the distribution is the Bernoulli distribution, with parameter p equal to 0.5. I can show its probability function on the computer. 2 columns, both the same height. What about a sample of size 2? If I toss 2 coins, what's the distribution of the total number of heads? The most likely number is 1, half of them, but you could get 0 or 2. What about a sample of size 10? We get more columns, but the peak is still in the middle. We're far more likely to get half the tosses 5 out of 10 to be heads than getting none out of 10 or 10 out of 10. Of course, this should be no surprise to you. The number of heads in 10 tosses of a coin has a binomial distribution, with n equal to 10 and p equal to 0.5. And the shape is very close to the shape of a normal distribution. Of course, there's an important difference in that the normal distribution is continuous and the binomial distribution is discrete. But we'll see later that's not a major problem. For the moment, let's just ask why we get this sort of shape. Why do we get this clumping in the middle? The answer's really quite simple. There's only one way of getting no heads in 10 tosses. That's all 10 tosses, tails. But there are lots of ways of getting 5 heads. In fact, 252 ways. And when the sample size gets larger, the number of ways of getting a value near the middle just becomes enormous. And that's why it doesn't really matter what the parent distribution is. Although the distribution you've chosen may be such that any individual arrangement giving a value in the middle may be unlikely, there are just so many different arrangements that the sheer number of them rapidly becomes the dominant factor. And that applies whether we're looking at the sum or the mean. Now, of course, that's a heuristic argument, and it's not intended to be a proof, but it is intended to convince you that we're arguing along the right lines. Another way of trying to convince you would be to do some simulations. We could take a parent distribution of our choice, take lots of simulated samples, and calculate the means. Then we could plot those means and see what the histogram of x bar looks like. Now, I've chosen a parent distribution which is designed to give the central limit theorem a severe test. Here's its PDF. You can see that it's asymmetric and U-shaped. It doesn't have a peak in the middle. Instead, it has a dip. What the computer is going to do is take samples of size 10 from this distribution and plot the mean. Here's the first sample, and its mean is 3.34. So we'll plot a block here. You can see we're using a group interval of 0.2. A second sample, and its mean is 2.04. As you'd expect, the individual values tend to be close to 0, or maybe close to 5, although that's not true for the mean. Now, I'll let the computer run on, and we'll see what our histogram looks like. You can see that there's variability. That's what you'd expect from a simulation. But you can also see that the columns are building up to something that looks rather like a normal distribution. We can check it by comparing it visually with a normal distribution. You can see that it's fairly close. In fact, that's about as good as you would expect with this kind of a simulation. And we can also ask the computer to calculate the skewness and the pointedness of the simulated data. Pretty close to 0 and pretty close to 3. In fact, the third good reason for expecting the sampling distribution to be close to normal comes from the formulae for skewness and pointedness. This was something we looked at in the last unit. We calculated the third and fourth central moments of the sampling distribution in terms of the third and fourth central moments of the parent distribution. Now, the skewness is the third central moment divided by the cube of the standard deviation. So, for the sampling distribution, we must divide by the cube of the standard deviation of the sampling distribution. The resulting expression contains a factor of 1 over n to the half. And what happens when n gets large? All the other terms are fixed, so the skewness gets very small. In the limit, when n approaches infinity, the skewness becomes 0. So, for a large sample size, we'd expect the sampling distribution to become symmetric, no matter how skewed the parent distribution was. And skewness 0 is one characteristic of the normal distribution. But what about pointedness 3? To get the pointedness, we divide the fourth central moment by the fourth power of the standard deviation. And again, it's the standard deviation of the sampling distribution, sigma to the fourth over n squared. And you should be able to see it coming. When n gets large, the first term contains a factor 1 over n. So it gets very small. And in the second term, n minus 1 over n is practically 1. So the second term gets closer and closer to 3. In the limit, as n approaches infinity, the pointedness of the sampling distribution approaches 3, no matter what the pointedness of the parent distribution. So that's another heuristic argument for accepting that the sampling distribution does become normal as the sample size gets larger. And although these arguments aren't proofs, I hope you'll find them convincing. But there is one area where you might be less than convinced. Let's go back to my first argument, looking at samples of coins being tossed. This was the probability function obtained for samples of 10 coins. And although we know that this is actually a binomial distribution, we said the shape looked quite close to being normal. But of course, the binomial distribution is discrete, and what we've plotted on the screen is its probability function. The normal distribution is continuous, and the curve we usually plot is the probability density function, a density rather than actual probabilities. We're comparing two different things. And is that something we can justify?
It is actually possible to compare a probability function with a probability density function, but a simpler way is to look at the cumulative distribution functions. Remember that the CDF has the same definition for both discrete and continuous random variables, so we can compare the two directly. This is the CDF of the binomial distribution, with n equal to 10 and p equal to 0.5. It's discontinuous because the binomial is discrete, and there's a jump at each integer, which is equal to the probability that x takes that particular value. If n were larger, there would be more jumps, but each jump would be smaller. What we want to do is to compare this CDF with the CDF of the normal distribution. We can plot both the CDFs on the same graph. As you can see, there's a good match. The normal CDF passes through each horizontal section of the binomial CDF. So, that's yet another demonstration that the central limit theorem applies in this case as well. Here we're applying it to a sum of n Bernoulli variates rather than a mean, because that's what is used for the binomial distribution. But we could equally well have applied it to the sample mean. However, for discrete distributions, there's one extra refinement which gives us a still better approximation. I'll show you how it works for this binomial distribution. Suppose we want to calculate the probability that x is less than or equal to 3. We can read this off the binomial CDF directly. Remember, we take the higher value for each jump, so the value at x equals 3 is about 0.17. Now, suppose we want to use the normal approximation instead. We could use the value of the normal CDF at x equals 3, which would give us about 0.10. So it's not a very good approximation when n equals 10. But let's look again at the two CDFs. You see that the normal always underestimates the binomial. It cuts each horizontal section of the binomial somewhere in the middle. So, if we want the binomial CDF for x equals 3, we get a much better approximation by taking the normal CDF halfway along the horizontal section at x equals 3.5. In fact, the difference between the two values is rather less than 1%. A correction like that is called a continuity correction. It gives us a much better approximation for any discrete variate when the sample size isn't very big. For example, let's look at the one you met in the pre-program notes. This distribution is highly skew, but we'll see how the normal distribution gives a reasonable approximation, and how the continuity correction makes the approximation even better. Here's the CDF of x bar for samples of size 2, and here's the CDF of the corresponding normal distribution. Not a very close fit, but for samples as small as 2, we wouldn't expect one. Now, here are the CDFs for samples of size 10. A much better fit. Quite impressive for such a small sample size and such a skew parent distribution. And once again, the normal CDF passes near the middle of each horizontal section. So again, applying a continuity correction will be well worthwhile.
Now, we started this program with a distribution that was discrete and about as far from normal as you could get. But as we've seen, the central limit theorem says that even if we don't know the parent distribution, the distribution of x bar is approximately normal. That means we can use the standard theory from Unit 11 to make inferences about the population. As an example, let's work out a 95% confidence interval for the mean number of purchases of cornflakes. Now, x bar is approximately normally distributed. In this case, we don't know sigma squared, the population variance. But let's see what we'd do if we did. This is the method you've met in Unit 11. We take the formula for the standardized variable, and we use that to calculate the 95% confidence interval. The interval is from x bar minus 1.96 sigma over root n to x bar plus 1.96 sigma over root n. But that's if we know sigma, the population standard deviation. In this case, we don't. But since n is large, sigma can't be very different from s, the sample standard deviation, which we can easily calculate. So we can make a further approximation, replacing sigma by s. Now we just have to fill in the numbers. N is the sample size. It's 491. The sample mean, x bar, is 3.43. The sample standard deviation, s, is 5.19. And if you do the calculation, the 95% confidence interval is from 2.97 to 3.89. So, we'd be 95% confident that the mean number of purchases was within this range.